tests of gravity quantumness. Please.
So good morning. I'm delighted to be the first speaker in person here. So I'm Vivishek Sudhir. I'm from MIT. I'm a faculty member there. I'm also part of the MIT LEGO group, but then we also do all sorts of other stuff outside of the purview of LEGO. So let's get started. I just wanted to give you, again, a fleshed out version of what Marcus was trying to tell us, which is that, let's imagine that, there's this massive object that's passed through some kind of a young double slit type experiment. And the idea is that, well, the particle actually either goes through A or B, and then there's a probability of landing up on the screen here, and then this probability actually has this, of course, this famous interference term, which manifests as, of course, the interference that we expect out of quantum mechanics if we believe that quantum mechanics actually applies to this large macroscopic object. Then, of course, you could try to do this, cunning thing where, well, because it's massive, perhaps as it goes through A or B, it probably produces a gravitational field near the slit. So let's try to sense that gravitational field, perhaps by putting a pendulum there, and then the pendulum swings either by an angle theta or an angle theta prime, depending on whether A or B is taken. So then in that case, you've got this idea that the quantum state of the joint mass and the pendulum is given by A theta plus B theta prime. And then if you then compute the probability, you see that, the interference term is now proportional to this overlap between theta and theta prime, which means that in fact, if theta and theta prime are perfectly distinguishable, as you would expect for a classical measurement of the pendulum, then of course the interference pattern completely vanishes, thus violating quantum mechanics for this macroscopic massive ball here, right? So the basic lesson is that if quantum mechanics is seen to hold for a large object, this sort of which path information should not actually be conveyed by gravity. And the standard sort of implication that people immediately jump to from this thought experiment is that, well, we believe quantum mechanics holds for this large object, therefore gravity should not be able to convey which path information, and then therefore gravity has to be quantum, in which case which path information is obscured by the quantum fluctuations in the gravitational field, right? So that's the sort of argument that goes forth. Now, if I really wanted to try to see whether which path information is actually present or not, what I should really do, as Feynman pointed out, is to actually close the interferometer, which is to say erase the which path information by projecting the state on a coherent superposition of the quantum state of the pendulum itself, and then I would really get back this state A plus B back again, so I'll basically recover interference in that closed interferometer, right? So, but the whole point of this is that this consistency of quantum mechanics for these large objects crucially relies on the fact that there is in fact gravitationally mediated entanglement between the mass that we send into the interferometer and some other device, such as this pendulum, that's actually used to try to gather this which path information, okay? And it's indeed this quantum fluctuation of the gravitational field which obscures the which path information. So really, this is sort of the motivation and palimpsest for the whole field in trying to go behind this idea of testing gravitationally mediated entanglement. So the idea then is that, well, if you take two harmonic oscillators separated by a distance r, there's this Newtonian gravitational interaction, which a careful calculation then shows that you can actually derive these kinds of things by doing tree-level computations in linear gravity. So it is sort of legitimately quantum in that sense. But of course, there's another way to actually think about the whole thing. Well, there are corrections to this Newtonian potential that can also be calculated famously by Donahue. And the idea is that, well, if you look at the magnitude of this correction term, this first quantum correction term, that is actually about 10 to the minus 60 times smaller than the dominant Newtonian term for distances of millimeter scale separations. Now, why is that hard? Well, 10 to the minus 60. Well, how hard is that in the context of what we can do experimentally? Always useful to look back at history. So here's really the history of essentially 100 years of people trying to measure the displacements of macroscopic objects, okay? So it really started in the 1920s. It was actually interestingly done by a Nobel laureate in biology. So Willem Einthoven invented the electrocardiogram, and in his Nobel speech, he basically said, you know what, if I try to make a very precise measurement of the electrometer wire, I see this wiggling, spontaneous fluctuation of the wire. So he was really observing the thermal Brownian motion of the electrometer wire in an ECG machine, okay? So that's one of these early experiments, and over time, of course, we've, let's say, largely in the field of cavity optomechanics, so that's since the year 2010 or so, perhaps a bit earlier, gained this enormous improvement in the precision with which we can actually measure the motion of mechanical oscillators. But the real issue is that in 100 years, we've only gotten 24 orders of magnitude improvement, whereas, if you wanted to go and measure this quantum correction to the Newtonian field, you need 60 orders in magnitude. So that's not happening in any of our lifetimes. That's enormously depressing for experimenters, right? Fine, so we go back and, well, ask ourselves, well, can we at least go and figure out this entanglement mediated by the Newtonian part of the interaction? So there's this gravitational coupling rate that you can write. I've basically introduced the 0-point motion of these mechanical oscillators, and then converted the x1, x2 into raising and lowering operators for the harmonic oscillator pendula. Okay. So I can then write down a gravitational coupling rate, which goes as big G, and then there's the mass. So the larger the mass, the better. The lower the frequency, the better. And of course, 1 over r cube, as Marcus was trying to motivate us. So really, the question here then is, well, can we prepare a pair of large enough masses in pure quantum states of motion, and actually bring them sufficiently close so that the effect of Newtonian gravity between them can actually be isolated reliably? Okay. So these kinds of experiments are actually fundamentally different from these class of experiments, which essentially, so the Colella-Overhauser-Werner experiment, and then there's this beautiful set of experiments done in Grenoble, where they actually measure do spectroscopy actually on a cold neutron beam standing in the Earth's gravitational field, okay? So you can actually do spectroscopy on it. Really cool stuff. And then there's this atomic fountain experiment where you can actually measure the gravitational acceleration due to a bunch of heavy tungsten masses, or the Ottawa style experiments that actually then measure Newtonian gravity. In all these experiments, what you do is actually use a quantum mechanical system to probe essentially a static gravitational field configuration. So these are not actually sufficient. What we really need is quantum mechanical bodies interacting with each other via the dynamical gravitational degree of freedom that are sourced by them, okay? So, in that spirit, the best you can do is, actually bring these masses actually arbitrarily close to each other, essentially touching, in which case, you can actually write down your gravitational interaction, the coherent part of that, as just being upper bounded by g times the mass density divided by the frequency, okay? And that number is the rate at which this coherent interaction happens, supposedly to produce entanglement, and that actually has to be compared against the dominant decoherence rate in the problem. And usually, when you think about mechanical oscillators, the dominant decoherence rate in the problem, after you've eliminated most of the technical, dirty stuff, is really the thermal decoherence of the test masses, so the thermal Brownian motion of the test masses, okay? And that actually goes as gamma, the decay rate of the mechanical oscillator, the classical decay rate, times n thermal, which is the average thermal occupation of the environment at some temperature T. So that's the Bose-Einstein occupation, okay? So you can actually figure out, what this dimensionless ratio actually looks like for various systems. Well, on the one hand, you would say, well, if I look at cold atomic clouds, well, they have low mass density, but perhaps that's compensated by the fact that they have extremely low thermal occupation, because you can actually cool them after all. But they also tend to have extremely low mechanical quality factors. So they actually, this ratio is 10 to the minus 26. Well, that's pretty daunting. So solid state mechanics actually are much, much better, about 10 orders of magnitude better, essentially because of their extremely high mass density, okay? And their extraordinarily high mechanical Q. So the mechanical Q of these mechanical oscillators can be million easily, whereas for these atomic clouds, they're typically in the hundreds. If anybody's interested, ask me why they're actually that low, and I'll tell you about it later. But of course, the problem with mechanical oscillators is that their thermal occupation is also extremely high, because they're sort of sitting there at 300 Kelvin, very hard to sort of get a handle on it. So that, if you wanted to do that, that's the 15 orders of magnitude that one really has to sort of cross to actually do any of these kinds of experiments. So it's really challenging. Interesting and impressive progress has been made, but still, we are still really essentially lacking this 15 or 10 orders of magnitude. So let's actually go back and ask a more, sort of precise question here. All that you needed to save quantum mechanics for this big object in this interference scenario is that which path information coming from gravity should actually not allow you to figure out through which slit the ball actually perhaps went through. So that's actually possible without gravity being quantum. It is in fact possible if gravity is classical, but in fact stochastic. Right? If you have a stochastic field, if it's fluctuating, you can actually look at the gravitational field, but it actually doesn't give you fundamental information about which path this thing actually perhaps went through. So really the question is, can we actually construct a pathology-free, consistent theory of classical gravity sourced by quantum objects? Okay, and this is sort of a long history. I'm not going to talk about the entire history of this problem, but the history of the problem is really replete with a whole bunch of no-go theorems and pathologies that come because the structure of quantum mechanics is actually extremely rigid. And by which, what I mean is that there are two big constraints. One is that if you try to introduce any nonlinearity in quantum mechanics, so for example, by taking the expectation value of, let's say, the stress energy tensor, in any such nonlinear modification of quantum mechanics would actually allow superluminal signaling. So that's something that all of us are uncomfortable with, so we don't want to have these nonlinear modifications to quantum mechanics. So here's one way to actually do this in a consistent fashion, and that's really an effort that was, as far as I know, first sort of promulgated by David Pula and John Preskill in a famous KITP talk. And then taken over by Jonathan Oppenheim, who's written a series of papers since then. In fact, I imagine he's going to talk more about this in his talk. So I'll keep it short to just a single slide here. And I urge you to go look at our work here. So really the idea is what you want to construct such a consistent theory is a joint state of quantum matter and classical gravity. So meaning that if I think about the phase space of gravity, and then there's some point z on this phase space, what I would like is that at each value of the gravitational field, that is the point z in phase space, I would like to be able to associate a quantum mechanical density matrix for the matter that actually sourced this gravitational field, right? So what this really means is that if I take this so-called joint quantum classical state, if I marginalize over the quantum degrees of freedom, I should basically get a classical probability distribution on the phase space. So that classical probability distribution basically describes the dynamics of the gravitational field. And if I marginalize over the classical degrees of freedom, I actually get back just the quantum state of the matter that actually produce these gravitational fields, right? And then what I really want is an equation of motion for the evolution of this joint classical quantum state that is actually pathology free. And you can actually do this construction, and what you see is that you get something like a Lindblad equation to begin with. So the evolution of this state, it's driven by some kind of Hamiltonian. There's a whole bunch of Lindbladian terms that come out, and then there is then a part that actually drives the classical state forward, and that actually looks very much like a Fokker-Planck style description. And in fact, you can identify this term. There are some constraints on these coefficients, and one of these constraints actually gives you that this first term, actually looks like a Poisson bracket with a classical Hamiltonian. Okay, so this actually, the second line is just a classical Hamiltonian plus some classical dissipation coming from these Fokker-Planck type terms. And then, of course, most importantly, what you have is an interaction between the classical and the quantum sector of this theory. Described by a whole bunch of functions m and these Lindblad operators L alpha. So really, that's the mathematical structure of this theory that comes out if you demand these constraints of being consistent with quantum mechanics. Okay, so this is not some microscopic construction of some theory of quantum gravity sort of slowly classicalizing. That's not what this is. This is just a top-down construction asking what is the mathematically consistent description of such a joint state that can exist without violating quantum mechanics. Okay, so that's what you get. So it's almost like the theorem of Lindblad in some sense. Okay, except for this quantum classical state. So what you really want then is, well, that's just the mathematical structure of such a theory. What you really then want is that this theory actually reproduces, once you marginalize over the quantum degrees of freedom, a classical description that is actually consistent with what we know about classical gravity, namely, let's say, general relativity. So in the Newtonian limit, this actually turns out to be reasonably easy to do. Jonathan will probably talk you through the technical morass that one has to deal with if you really want to do this in full covariant GR, because, well, then the construction of the phase space itself is, extremely technical. But in any case, what you end up with after you do all the hard work and sort of, marginalize the gravitational field is you actually end up with a closed equation of motion just for the density matrix of the quantum degrees of freedom in the problem, and that is actually fairly, you can actually stare at this and make sense of what's going on here. So the first term is actually fairly easy. There's the Hamiltonian. Then there's the coherent Newtonian part of the interaction. That's exactly your GMM by R square. And then, interestingly enough, there's an additional term that actually comes up as a dissipation on the quantum mechanical part of the density matrix, which is not the standard, decoherence that you see in Dioschi-Penrose style models. This is actually slightly different, and I'll tell you why that is. So in any case, what you have really is this joint dissipation term, joint decoherence term, we call it, which is also proportional to the 0, part of the stress energy tensor. There's the gravitational constant, and then there's this, constant epsilon, dimensionless constant epsilon, that is actually a free parameter in this theory. Okay, so epsilon could be anything, except, of course, if epsilon is 0, this entire term is absent, and all you're left with is a quantum theory of these objects interacting via the quantized Newtonian interaction. Okay, so that's kind of nice. So epsilon equal to 0 gives you essentially what one would expect out of a quantum theory of gravity in the Newtonian limit, entanglement, so on and so forth. And if epsilon is finite, you get this additional decoherence. So really, the job of experiments is to then go and sort of figure out what this value of epsilon is, right? In fact, this Lindbladian is sort of extremely natural in the sense that if you just try to write down Lindbladian, the only dimensional constant at this order of magnitude that you can write down is gm squared by d. So d is basically the distance between these two things, and then there are two operators that basically have to be proportional, that have to be functions of just the difference in the mass of these two objects, because you want the theory to be translation invariant. And then in the Newtonian limit, you want these guys to actually look something like some epsilon I times x1 minus x2. So that's just Taylor expanding this and dropping the trivial term, the trivial constant term. And if you then write this out, what you get is terms that actually look like that. So the first term, which actually looks like xi rho, that is just the decoherence of the individual masses in this theory, which we don't really care about. But importantly, what you get is a term that looks like x1, x2 rho, which then tells you that there is some decoherence that is actually joint between the two masses that actually source the gravitational field. Okay, and that's exactly by reducing this, you can actually show that that's exactly this. So in some sense, this term is just, you can do dimensional analysis. You could have just done dimensional analysis to actually get at this term. Okay, you didn't have to do all this complicated technical construction anyway. So that's that. So what is required then to shoot down these class of theories is, you can actually go take this master equation and sort of figure out what is it that it bodes for an actual experiment. And what we've done here is actually imagine an experiment where there are two masses sort of interacting with each other via this theory, and then look at the cross correlations between the displacement fluctuations of these two masses. Okay. So depending on whether gravity, the intervening gravity is classical or quantum, there's a clear signature of what happens to the displacement fluctuations of these two masses. Okay, the correlation in the displacement fluctuations. So what I show here is the power spectrum of the correlation of the displacements of the two masses. And importantly, if I zoom in very hard at the middle, so this peak actually, of course, just comes from the fact that these two are mechanical oscillators, so there's a resonance. But if I look hard at the middle, you see that the quantum case corresponds to epsilon equals 0, and that's basically the dotted line here. And the classical case is basically, let's say, epsilon equals 1, and that's the solid line here. And because the correlation is a complex quantity, it has got a magnitude and a phase. So the red is actually the magnitude here, blue is the phase. And in the classical case, you actually see that there's a phase inversion. So in fact, in principle, which is actually completely absent in the quantum case. So in principle, if you could actually do this experiment where you go and look for the inversion of this phase, it is a decisive test of whether gravity is classical or not. Okay, so it can actually be ruled out without actually looking for things such as mystery decoherence of some macroscopic object. And looking for mystery decoherence of a macroscopic object is a very bad idea, right? Because as an experimenter, mystery decoherence is everywhere. So just because a theory predicts mystery decoherence is not something that as an experimenter I'm motivated to go search for it. That's just not going to happen. Okay? So I challenge essentially theorists to actually come up with decisive predictions that can actually be tested, not mystery decoherence. And this here is one example. So right, so what we need then is a pair of large masses in nearly pure quantum states of motion with their interaction dominated by mutual gravity, and we don't crucially require the gravitational interaction to be comparable to the thermal decoherence rate of these masses. Something actually much less is actually sufficient. So that's something that, you don't need to bridge some 10 orders of magnitude in experiments. You can perhaps go do this in still, let's say, 5-10 years, okay? You don't need 30 years, perhaps. So right, so what is the state of the art in preparing large masses in nearly pure quantum states of motion? So again, here's perhaps a scale that's longer than Marcus's scale here. So what is it, 35 orders of magnitude in mass. So at low masses, this is the regime of atomic physics and so on. This is the regime, so this is sort of experiments that Marcus was sort of telling you about, these levitated nano beads. So they sort of lie somewhere here, where quantum states of motion have actually been realized in the past, let's say 10-ish years. And on the other end of the scale is the scale at which gravity has sort of been measured, but quantum states of motion of such large objects have not been realized. So what is the problem? Why is it so hard to realize quantum states of motion of such large objects? What is the technical problem here? Is it just that experimenters don't have enough money, or is there something fundamentally different? In fact, the answer is that there is something fundamentally different when you think about large masses. So the standard way in which you prepare the state of these objects such as nano beads, nano beams in cavity optomechanics, atoms, BECs, ions, things like that, is by this process called resolved sideband cooling. So you have some kind of a particle in some kind of harmonic oscillator. Perhaps it's got some internal two-level state that it couples to, or perhaps there's some cavity mode that it couples to, such as in cavity optomechanics. And then there is this interaction that you can write that linearly couples the harmonic oscillator mode to some internal mode here. So there's some cavity profile, and then you bring your laser or some other coherent excitation, essentially one mechanical frequency down from that cavity resonance. And then when there is preferential scattering of photons from the laser beam to inside the cavity, that must have happened at the expense of a h bar omega m of energy. So therefore you're losing energy from your mechanical mode, thereby cooling it. Of course, the point is there's also some not so preferential, but still non-negligible scattering onto the other side, which is sort of a competing heating process. So the equilibrium, the detailed balance between the cooling and the heating process actually gives you the equilibrium temperature here. And if you look at the expressions for these things, that equilibrium is basically given by the ratio of the density of states on the upper side divided by the density of states on the lower side. So in this particular picture that I'm showing you, well, that ratio is large because I can actually have a mechanical frequency, because the object is small, that is much, much larger than typical cavity frequencies that I can get, and therefore I can get extremely large suppression of this asymmetry, and I can actually do this cooling effectively. But of course, as mechanical oscillators become large, and the stiffness of springs by which they're suspended remain essentially the same number, this mechanical frequency drops drastically, meaning that you're now thinking of parking your laser somewhere here, which means that now there is no asymmetry in the density of states. So laser cooling is really out of the window from the get-go. However, there is some saving grace here. So if I think of a mechanical oscillator sitting in some good vacuum, and if I think about the damping coming from the gas molecule sort of hitting it, I would have a susceptibility of the mechanical oscillator that looks like that. So this is just the Fourier transform of Newton's equation of motion, where this damping term now looks like some I times the Fourier frequency times some damping rate. So that's called velocity proportional damping, because it really did come from a term that looks like dx dt. But at some point, of course, as I evacuate the gas more and more, this velocity proportional damping is sort of going to go away, and I'm going to be limited by, in fact, damping in the very spring that actually holds my mechanical oscillator, okay? Because as the spring expands and contracts, it need not actually come back to the same point as it does its cyclic motion, right? So there can be some hysteresis in the spring, phenomena that's actually called anelasticity, and you can actually have energy loss in the anelastic response of a spring, of the suspension spring. And that is what, in this field, we call structural damping. So that can be modeled effectively as an imaginary part of the mechanical frequency, because it really comes from an imaginary part in the stiffness of the spring, okay? So that's loss. So if you now look at the thermal motion, the thermal Brownian motion of such a anelastically damped harmonic oscillator, what you see is that compared to a velocity damped oscillator, which is this yellow thing here, above resonance, for an anelastically damped spring, mechanical oscillator, you actually have a significant drop-off in its thermal motion, thermal Brownian motion, compared to the velocity damped case. So in fact, this means that if I'm able to actually take this mechanical oscillator low frequency and then sort of apply a lossless spring to it to actually bring it to these high frequencies, then I can actually take advantage of this decreased damping at higher frequencies compared to a velocity damped spring. And in fact, you get a quadratic reduction in the decoherence rate of the mechanical oscillator because of this effect. So that's actually pretty nice. And you can actually go and figure out the quantum theory of cooling under these conditions, and that's basically what this paper is here about. So how do we actually utilize this? Well, one way to utilize this is using this idea of so-called feedback cooling. So you have this mechanical oscillator, perhaps it's measured using some kind of an interferometer. So the displacement x of this mechanical oscillator transduces into some phase of the outgoing light, which you measure. But of course, the measurement is always imperfect, even from a quantum mechanical standpoint. So what you get is the phase signal that you would like, plus some uncertainty, perhaps coming from the fact that light itself is a quantum mechanical entity, and it has to have some fundamental phase fluctuations, okay? So that's basically what this is. So if I look at the sort of quantum optics picture of light, I see this blob that comes from the vacuum state of the light, which then subtends a certain angle, which actually goes as 1 over the square root of the number of photons. So I would like to make this uncertainty small by increasing the number of photons that I use to make this measurement. But of course, as I do it, remember that light, of course, again, due to complementarity, is just a bunch of particles. So there's going to be a fluctuating force because of the photon recoil fluctuations at the mirror, right? So it's the quantum back action of this measurement, basically. And the product of these two things, of course, you don't win. That's basically the problem, which is Heisenberg's microscope. However, you can still use this measurement to then apply a feedback force, if you will, in a sufficiently noiseless fashion, if you can, to actually damp and cool the motion of this mechanical oscillator. And in fact, it turns out, importantly, that for a structurally damped mechanical oscillator, the requirements to do feedback cooling to the ground state are actually much less compared to the requirements to do this for a velocity damped oscillator. In particular, the mechanical quality need not be as large as the thermal occupation, which can be very large for these low frequency objects. It can be reduced by the cube of this standard quantum limit frequency. So it's some large number, that's all I'll say here. And the measurement imprecision does not need to be n thermal times smaller than the 0-point motion of the mechanical oscillator. It only needs to be n thermal to the 2/3 smaller than the 0-point motion. So again, these are really nice tools that you can actually harness. So we can actually do this in the largest mechanical oscillator that we can actually coherently control today, which are the 10 kilogram masses, in fact 40 kilogram masses in LIGO. So that's an example of one of these 40 kilogram masses suspended as a harmonic pendulum. And then there's the interferometer that's actually, of course, built precisely to make the most exquisite measurement of the motion of these test masses, right? So the interferometer, it's pumped by a laser, it's a microsound interferometer, there's a Fabry-Perot cavity to enhance the sensitivity, and then what you measure is the light leaking out of the antisymmetric port of this beam splitter, which then gives you a measurement of the displacement of this mirror. So to zoom in a bit further and abstract out a bit, that's what the interferometer looks like. So the test masses are really these, 40 kilogram human scale mirrors. They suspend, because of their mass, as 0.5 hertz pendula, okay? And they're suspended from glass wires that are as thin as 400 nanometers, okay? So really, amazing feat of engineering. And really, that's a standard human. So it's about my size. It's not a child. Okay. So that's really a human scale mechanical object. I can go touch it, although I would never want to. Right, so that's basically what it is. Again, another standard human being there. Of course, if I look at what prevents us from making a very good measurement of the displacement fluctuations of this object, of course, one is that the mirror itself has its thermal Brownian motion that I was trying to tell you about. And then, of course, there's this mirror coating on these mirrors. So if I think about the mirror coating, well, these are these, micron scale alternating stacks of dielectrics that are there to actually reflect the light back as perfectly as possible. But of course, the problem in LIGO at present, by and large, is that the interfaces between these coatings is actually not as clean as we would like. So mechanical loss in the interface actually causes motion at the interface. So the thickness fluctuations of this, I don't know, 10 micron stack reflective coating on the mirror is, in fact, a primary limiting factor in the sensitivity of LIGO. Okay? So that's called coating Brownian noise. And then, of course, there is quantum back action. Well, you might say, well, why are we worrying about quantum back action on a 40-kilogram mirror? Well, the reason is that the optical power that's actually used in LIGO in the arm cavity is about 250 kilowatts. Okay, so it's not I would say it's not a grad student safe experiment in some sense. Right? If you put your finger in there, you're going to get a bad burn at best. Right. So LIGO is in fact in a regime where the quantum mechanical interaction of the radiation pressure force acting on the mechanical mirror, even a 40-kilogram mirror, actually starts to be interesting and important. Okay? So it's probably the world's largest macroscopic mechanical system in that sense. So of course now LIGO has sort of been enhanced, its sensitivity is enhanced by the employment of squeezed light to actually get an optimal trade-off between the uncertainty in the measurement of the phase and the back action acting on the mirror. Okay? So if I look at the sensitivity of LIGO, that's what it looks like typically. So this, the red line is basically the sensitivity that I have. It's about, in displacement, it's about 10 to the minus 20 meters. So that's the pink line there. If I use squeezing, 3 dB of squeezing, that actually gets me down by another 3 dB there. So that's the dark red line. And then the gray line is basically the sum of all the classical noises. Okay? All the non-quantum noises. And if I look at very low frequencies, so at around 0.5 hertz, I actually see the pendulum mode undergoing its Brownian motion. And my job really is to make sure that the pendulum mode is stiffened to the most sensitive band in LIGO so that we can actually then harness this reduced requirement for feedback cooling the motion of this test mass. Okay? So that can actually be done. So you make a measurement. There's the measurement record, which you can cast as the displacement, the actual physical displacement, plus some uncertainty in the measurement of the displacement. And the intrinsic motion is basically given by the thermal force and the back action force and the intrinsic susceptibility of the mechanical oscillator. So that's just the response function. And then I close the feedback loop. And then the feedback force is something that I actually add here. But the feedback force is synthesized from the actual measurement that I made. So there's an additional feedback filter. And then there's the actual physical measurement that actually I measured, but then there's also this uncertainty in the measurement that actually now comes from quantum fluctuations in the measurement. So I can close the feedback loop, and my job really is to do, essentially a classical job in some sense. I need to do a very good job of designing this filter to actually trap the mechanical mode and cool it while making sure that the interferometer remains completely stable. Okay, so that's a job that a well-trained classical electrical engineer could actually do. Okay, except here's the catch: you want to do this while making sure that the quantum noise in the problem also remains minimal, and that's where a classical electrical engineer may not actually even know how to think about this constraint, and that's why we still need quantum engineers perhaps. So, but we can do that. And here's the sum of everything. After we do that, so that's actually a 0.5 hertz mechanical oscillator, which has now been trapped around a frequency of 150 hertz using an optical spring. And then we basically designed the feedback filter in such a way that you actually dampen cool the motion of this guy down. Okay. And this mechanical oscillator, let me remind you, starts from an ambient thermal occupation of 10 to the 9 phonons at 300 Kelvin. Okay. And it has now been cooled down to near its ground state. So this actually corresponds to a thermal occupation of something like 10, which corresponds to an average mode temperature of something like 77 nanokelvin. Okay, so that's a 10 kilogram object sort of spending 10% of its time in its quantum ground state. Okay, so fairly macroscopic. But of course, even though we can do that, that's an excellent test of this idea that you can actually do feedback cooling of extraordinarily large objects. That's actually not actually sufficient to for the purposes of interest here, which is to actually study this gravitational interaction or perhaps falsify this classical quantum theory of gravity. What we require then is exactly the kinds of experiments that Marcus was actually hinting at, which is that you want to have mechanical oscillators, source masses that are, let's say, milligram scale masses, sort of gravitationally interacting with each other while their motions are actually measured and controlled at the level of their quantum zero-point motion. Okay, so how do we do that? So here's one way to do that that we've been pursuing in our group. So we've actually been making these centimeter scale torsional oscillators. So that's a thing again. You can actually hold in your hand, see the 1 centimeter long object. It's made of highly stressed silicon nitride, and there's an effect in silicon highly stressed mechanical materials, dielectric materials, called stress dilution, whereby the mechanical quality of the resulting stressed object can actually be much, much larger, in this case about 10 million, much larger than the let's say 10 to the 3 or 10 to the 4 that you can get natively out of the bulk loss in this material. So that's an interesting effect that's been known in the community for a while now. So we exploit that. We can actually measure the mechanical quality of this thing. This is basically the measured ring down of this object in its fundamental mode as I give it a kick. And I can go get a nice shot of espresso over the 10 minutes that it takes for this to actually ring down, right? So it's kind of cool. So now we need to actually make a measurement of this torsional oscillator. So the way to think about this is, you go back to your quantum optics and remember that in fact light that comes in, I prepare light in its coherent state, in its fundamental mode, but of course there are vacuum fluctuations in its higher order mode. So these are the higher order Hermite-Gauss modes for people who are sort of familiar with optics. So when the light actually reflects back from a pendulum, what I get is actually the same mode back, more or less, except there's a small amount of scatter, so that's proportional to the amplitude in the fundamental mode, but it actually carries information about the angular motion of the mechanical oscillator, and there's the GUI phase that actually it basically accounts for the free space propagation of this higher order mode along the downstream path. And for simplicity, for completeness actually, I've added also the possibility that there's some transverse displacement of the torsion pendulum in that plane. It's actually important because both these objects, the transverse displacement and the angular motion, they are good proxies for the quantum mechanical quadratures of the reflected higher order field. So what this means is that in this phase space picture, if I had an angular motion at the beam's spot focus over a GUI phase of pi/2, that angular motion would actually get converted to a beam displacement fluctuation in the far field. And this I can actually go and measure with a split photodiode. But of course the problem is, all of this is obscured if there is spatial mode noise in the beam that I use to make this measurement. So this is basically the sort of the nuts and bolts and the dirtiness of precision measurements. Okay. So we actually have a technique to actually eliminate this classical noise. In the interest of time, I'll actually flip through it. It basically involves using something like a Michelson interferometer. So you see this second arm here, but it's not really an interferometer. But in any case, what we can do is actually get more than 60 dB of suppression of classical spatial mode noises by using this kind of topology here. But of course, the other problem is when you do measurements, extremely precise measurements of the fluctuation of an optical beam, you really care about drifts in the temperature of the lab, as Marcos was trying to explain, right? So we've actually constructed a lab specifically at MIT, which is sort of, isolated. It's sort of like a Russian doll. There's 3 layers of isolation for the entire lab space, and the air inside the lab is actually, its temperature is actively stabilized and controlled, okay? And once you do that, what you see here is, this is a measurement of the Allen deviation of the temperature in the lab, across the lab, so across, I don't know, 2.5 meters, something like that, over averaging time. And what you see is that when the controller is actually on, the average temperature across the lab can be stabilized to a precision of about less than 10 millikelvin. So if I say that I want a temperature of the lab to be 20 C, it'll be 20 plus or minus 10 millikelvin, okay? That's how precise it can be. And once that's done, you can actually run this optical measurement, and you can actually measure angular displacements at the level of picoradians per root hertz, essentially limited by quantum fluctuations of the light in the higher order mode above frequencies of 1 kilohertz. Marcus was telling us that he for his gravity measurements he had a optical lever that was sensitive at the level of a nanometer, nanoradian, I suppose. So this is probably 1,000 times better than his thing. And once you have this measurement, you can actually go and cast this measurement in terms of the standard quantum limit for the measurement of angular displacement of this 1 centimeter scale torsional pendulum, and we can actually get a measurement precision which is about 13 dB smaller than the standard quantum limit, okay? And the standard quantum limit, of course, just to remind you, comes from the trade-off between the zero-point motion of the mechanical oscillator and the Heisenberg uncertainty principle that actually constrains the product of the measurement imprecision and the back action. And that, once you do the math, it actually is proportional to the zero-point motion. It's a bit more than the zero-point motion. And once you have that measurement, you can actually go do almost something similar, which is to actually do feedback cool this centimeter scale object. We can actually feedback cool it from room temperature, so about 10 to the 8 phonons, to something like 5,000 phonons. So the reason we're not actually good enough here is because the measurement sensitivity is simply not good enough. So we need to actually work a bit hard on getting this measurement sensitivity up, and we have some ideas for how to do that. So really what I've tried to impress upon you is the idea that really macroscopic objects, human scale objects, tangible objects that you can actually touch and sort of feel with your finger, they can actually be prepared in quantum states of their motion. And that is sort of a fundamental starting point for doing all these kinds of other experiments in a regime that is actually very different from the regime that Marcus was talking about, okay? So with that, I'd like to thank you for your patience and attention and the invitation to actually speak here. Thank you.
We have some time for questions. I have one, since no one raised. Yeah, I mean, you mentioned in a previous slide, in one of the first slides, you mentioned, you said the sentence, you have to isolate the two masses so they interact gravitationally only with each other.
Predominantly.
Okay, because that's sort of impossible, isn't
Yeah,
it?
what I meant is predominantly.
Even if you take it to space, you
You need to be in a regime where their dominant interaction is gravitational. That's what I meant.
Fair enough, but they will continue interacting with the Earth, and this is also a source of decoherence.
Absolutely.
Yeah. Okay.
So in fact, those are channels of decoherence that one has to really worry about when you bring these things close together. But that's not even the most sort of prescient decoherence channels. When you bring these two things close together, they're actually extraneous electrical field fluctuations and things of that sort.
Questions? Yeah.
Just following up, does any of those experiments ever take into account Earth gravitational field effects?
Yeah. So in fact, so for our experiment, it doesn't matter, because if you look at the frequency, it's about 36 kilohertz, and at 36 kilohertz, there are not. I mean, we've actually sufficiently well isolated. In fact, it is easy to isolate seismic vibrations at 36 kilohertz. For LIGO, it's a huge problem. In fact, in LIGO, I can tell you that at 0.5 hertz and 0.1 hertz, the real issue is that when there's an earthquake happening somewhere very, very far, it's not the direct sort of ground motion of the earthquake that actually causes the problem. That can actually be isolated to a certain extent. What is really a problem is there's what is called a Rayleigh wave. It's a specific kind of wave that actually happens in the soil, understood as an elastic continuum, something called a Rayleigh wave, which actually then produces a density fluctuation of the soil as it moves. And that density fluctuation is now a oscillating mass that actually applies a direct Newtonian force on the 10 kilogram test mass. Okay? So you get what is called gravity, Newtonian gravity noise, which you can't actually shield from because it's gravity, right? So that's a problem for LIGO, and in fact will continue to be a problem for future iterations of LIGO. But yeah, there are some ways to actually deal with it to a certain extent, but not quite.
Yes.
Hi, thanks for the talk. I have a very naive question.
Sure.
So you're testing, or one part of your proposal is to test whether gravity is, has a quantum nature or not. And for those believers that gravity has a quantum nature, one of the big problems that we want to address is the fate of singularities, for instance, black hole singularities.
So the black hole information problem, basically.
Well, yeah, evaporation of black holes singular. So for those of you that, still question whether gravity need to be quantized, what is the thoughts that you have on that?
Yeah, sure. So in fact, I was talking to Gautam about exactly this problem while we were having coffee. So I was trying to impress upon him the need to actually use some consistent theory of classical gravity to see, what actually that bodes for the information problem. It complicates the problem. It doesn't offer any direct resolution, because even in classical physics, you have this idea that information cannot be lost. It's just Liouville's theorem, right? So just because quantum mechanics is unitary is not the reason why information should not be lost. Information cannot be lost even in a closed classical system because of Liouville's theorem. So if you now suggest, as I'm sort of, perhaps wanting to suggest, that gravity is classical, it doesn't offer an immediate solution to the problem. It just complicates the problem a bit more, and somebody has to think about it. And if you want to be the person thinking about it, go for it.
All right. Fortunately, we're kind of running late. So, thank you very, very much. The next speaker is So here's the microphone and this thing here. Yeah, this.
So where does that go? In my pocket.
This goes either here or.